The rapid growth of the IoT has revolutionized industries by enabling smart devices to collect, process, and exchange data in real time. IoT hardware, which includes sensors, microcontrollers, embedded systems, and communication modules, is the foundation of these interconnected systems. However, despite their benefits, IoT devices often suffer hardware limitations, such as low computational power, limited memory, and constrained energy sources. These limitations make it challenging to implement robust security measures, leaving IoT systems vulnerable to cyber threats. Attackers can exploit weak encryption, unsecured firmware, and poor authentication mechanisms to compromise device integrity, disrupt operations, and gain unauthorized access to sensitive data. As IoT devices become more integrated into critical sectors such as healthcare, transportation, and energy, the importance of cybersecurity in IoT hardware has never been greater. Security risks, including botnet attacks, wireless jamming, malware infections, and physical tampering, pose significant threats to individuals and organizations. Addressing these risks requires a multi-layered security approach that includes strong cryptographic algorithms, secure boot mechanisms, firmware integrity verification, and continuous monitoring. Additionally, manufacturers and stakeholders must prioritize cybersecurity by enforcing strict hardware security policies, implementing regular updates, and adopting proactive defense strategies to safeguard IoT ecosystems from evolving cyber threats. IoT hardware vulnerabilities can be categorized into 4 categories, which include cryptographic algorithms such as encryption, tokenization, and masking play a crucial role in ensuring the confidentiality of IoT data. Additionally, robust authentication and access control mechanisms are essential to restrict unauthorized access. However, several vulnerabilities exist in cryptographic, authentication, and access control implementations, including weak cryptography. Limited computing power prevents strong encryption, making devices susceptible to attacks. Manufacturer oversights. Default passwords and poor authentication mechanisms expose devices to unauthorized access. Firmware tampering. Ineffective verification allows attackers to manipulate firmware, compromising security. IoT networking and communications infrastructure is particularly vulnerable to cyber attacks due to its constant internet connectivity, resource constraints, and ease of compromise. These factors make IoT devices an attractive target for attackers. Some standard IoT network and communication vulnerabilities include shared communication channels. Packet collisions disrupt communication in shared channels and drain energy in case of attack. Wireless jamming attacks. Attackers jam wireless signals, forcing devices to drain energy rapidly. Flooding attacks. They involved overwhelming IoT devices with useless packets to deplete resources and disrupt functionality. Route poisoning. It involves the manipulation of routing paths to create inefficiencies, leading to energy exhaustion. Botnet vulnerabilities. This involves potentially using infected devices to launch large-scale DDoS attacks. Effective IoT device management is crucial for identifying and mitigating security threats and vulnerabilities before they can be exploited in an attack. It also enables the rapid detection and response to potential IoT security incidents. However, poor device management remains a significant challenge, leading to various vulnerabilities in IoT devices and networks. Some of the key vulnerabilities related to IoT device management include lack of visibility. Devices without proper identification create security blind spots. Poor device management. Failing to update firmware and apply patches exposes devices to cyber threats. Persistent hardware weakness. Vulnerabilities such as side channel attacks and hardware reverse engineering persist over time. Devices are vulnerable to physical attacks such as tampering, vandalism, and unauthorized manual access. The strategies required to mitigate IoT hardware vulnerabilities include the following. Manufacturers should incorporate lightweight encryption algorithms such as AES-128 and ECC to mitigate weak cryptography, which provides robust security with minimal computational overhead. Implementing secure boot mechanisms ensures that only authenticated firmware is loaded, preventing firmware tampering. Furthermore, replacing default passwords with unique, strong credentials and implementing multi-factor authentication enhances device security. To protect against wireless jamming and packet collision attacks, IoT systems should use frequency hopping spread spectrum and direct sequence spread spectrum techniques. Deploying firewalls and intrusion detection systems can detect and mitigate flooding attacks and botnet activities. Secure routing protocols should also be enforced to prevent route poisoning and ensure efficient network traffic management. Regular firmware updates and patch management are critical to addressing newly discovered vulnerabilities. Automated over-the-air updates should be implemented to ensure all devices receive the latest security patches. Network segmentation can limit the impact of an attack by isolating compromised devices, while continuous monitoring and logging help detect abnormal behavior, reducing security blind spots. Physical security measures. IoT devices should be equipped with tamper-resistant hardware and secure enclosures to prevent physical attacks. Deploying geofencing and location-based authentication can prevent unauthorized access to devices in sensitive areas. Physical security measures such as surveillance cameras and biometric access controls should also be implemented in critical environments to prevent unauthorized handling. By addressing these vulnerabilities through hardware improvements, cryptographic solutions, proactive management, and strong physical security measures, organizations can significantly enhance the security and resilience of their IoT systems.